the stepping actions, I mean, step over, step into, step out. Perhaps you know how to modify the variable values using the debug window, even if you do not have access to its source code. Or do you? But you know what bugs do? They like to play hide and seek. But don't worry, we have many more ways to find those hidden bugs in IntelliJ IDEA, such as method and exception breakpoints, object marking, memory debugging. My favorite, stream debuggers. Oh, you want to know what these are and how to use them? To do that, we have a very special presenter with us today. Hi, everyone. Thanks for joining in for another episode of IntelliJ IDEA Livestream. I'm your host, Mala Gupta, and today I'm very pleased to welcome Shai Almog.
Hi.
Hi, Shai. It's a pleasure to have you present with us today.
Thank you for having me.
Oh, I'm so looking forward to learn from you today. And everyone who doesn't know Shai, let me quickly introduce him. He is an author. He has written 5 books, including Practical Debugging at Scale. So you know you're talking with the expert today. He's an entrepreneur, open source hacker, and you would find him blogging about debugging at Debug Agent. So I've been reading your blogs also, Shai, and this is how I really wanted to have you with us on this uh, event. What I sorry, lots of words here.
It's great to be here on this channel. It's been
Thank you
looking
so
forward
much.
to it.
So, Shai, before I let you take the stage, I want to ask you a quick question because you mentioned that you have been presenting this session at various conferences and events. So, what is that the audience comes to you after you are done presenting with your session and they talk about some of the features? They say, "Wow, that was amazing. We didn't know it existed, and it is very helpful." So, some of your favorites.
So that's a great question because the answer is kind of surprising to me. My favorite features from this talk are object markers, renders, stuff like that. The very geeky stuff, the very things that people who are deeply versed in debugging find really exciting. But the feedback that I got from people was that things like Tracepoints, or known also as log points, they didn't know about them. And for me, that's something that is very useful, that I use every day. So I don't really appreciate it as much as people who weren't familiar with that. It's something that I took for granted. But when people came to me and were amazed by how it changed their debugging process, that really struck a nerve that, maybe it's an outlook of a geek in the debugging industry rather than what people find super useful. Still, I think everything that I'm going to talk about is interesting and useful, but sometimes the simplest stuff that you don't know about is revelation.
And absolutely, what all you said, it makes so much sense because that applies to me as well when I talk about a lot of new Java features at conferences. People come up to me and they talk about things which I would kind of assume they would know, but they would talk about things, oh, we didn't know this existed in Java or IntelliJ IDEA. And that is, again, I have the similar thoughts as you say. So I'll not take a lot of your time. And before I let you take the stage, let me share some quick housekeeping details for everyone who's watching this session today. Please use the YouTube chat to post your questions. You don't have to wait till the end of the session to post your questions. Shai would answer your questions as he's presenting the session. And we also have developer from JetBrains to answer your questions. And yes, the most important question, the session is being recorded and hosted on IntelliJ IDEA's YouTube channel and also on Twitch channel. So if you haven't already subscribed to both these channels, now is the time to do so. Last, not the least, if you like today's session, which I'm very sure you would definitely do not miss to like the video. And with that, Shai, let me add your screen to the stream. And I'll be backstage, and all the best for your session.
Thank you. So, hello everyone. So, as we mentioned before, I'm Shai Almog, and almost 30 years ago, I got lucky. I was sure I was a great programmer. Then I had a debugging session with a senior developer, and I was completely floored by the way he wielded the debugger. He used features and techniques that I was totally unaware of. I had no idea. And I felt a bit humiliated that I didn't know these things. All of that self-doubt came up, and I vowed to do better. And I did. We don't learn debugging in university because they can't test that knowledge. A tool we spend so much time inside on our day-to-day job is essentially left as a take-home exercise. I was lucky to get a glimpse of competence that made me study this tool and the surrounding process. Hopefully, I can pass some of that luck on to you. But before we proceed, let me say a couple of things about me. I worked at a lot of companies, including Sun and Oracle. I founded a couple of companies, wrote a lot of open source code, and I recently published 3 separate books. I hope you check them out and follow me on socials listed here to learn more. As Mala mentioned, I wrote a book about debugging, which was published by Apress. This entire talk is based on part of the first chapter in that book. So check it out, and also check my YouTube channel, which includes lots of additional material and a lot of lectures about debugging. Without that out of the way, I want to jump right into the features that are inherent in IntelliJ IDEA, which will comprise the entirety of this specific talk. The first one I want to talk about is force return. It lets us return immediately from a method and potentially return a different result from the method. So when we're experiencing a problem, we can return fake data from a specific method to simulate a problematic condition. Unlike step out, we return from this point while skipping the rest of the method. We type in the return value, and the rest of the code won't execute. This lets us change the control flow of the app. We can return different results or skip problematic code to see what happens next. Imagine a case of a hard-to-reproduce bug. This means we can simulate the condition that can trigger that bug. I can return a dummy object from a method to simulate an edge case we saw in production logs. And that way I can reproduce something that's normally a not reproducible bug. But this gets better. We can actually move the current instruction pointer to a different position in the method. In IntelliJ, we need to install the jump to line plugin for this to work. This is an amazing feature and remarkably underutilized. I know people don't know about this feature because the install numbers for this plugin are sadly very low. Once the plugin is installed, we can drag the arrow on the left to bring execution to a new location. If you saw a bug, just drag the execution back and reproduce it. We can skip over code that's failing, etc. Imagine building a unit test. Just drag the execution point back and forth and tune the variables you passed into the method. That way, you can get a sense of the right arguments you need to pass to get good coverage. I use this a lot when working on unit tests to improve coverage. I just go back and try again with slightly different values to get higher numbers. It's the ultimate do-over button, and you don't need to stop, recompile, or anything like that. A watch point is a breakpoint we can place on a field. This is pretty standard, but a surprising number of people aren't aware of that capability. We can place a watch point on a field, which will stop every time the value of the field changes. This is a remarkably cool way to catch a case where some code mutates a variable. We can tune this so it stops not just for changes to the field, but for reading the value of the field, or only for reading the value of the field. Normally we have getters and setters, but not always. Find usage is also very useful, but some variables might be accessed from many sources. With this feature, we can narrow down the specific code responsible for the mutation. Notice that you can use conditional watch points to stop only when the field is set to a specific value. Tracepoints are probably the most important yet unknown feature of debuggers, as we discussed earlier. Tracepoints are often called log points. They're a special type of breakpoint that doesn't break. They don't stop the execution. Typically, they just log to the console. You can add a tracepoint by shift-click on the gutter, the left side of the IDE. Notice I can write any valid expression here, either a string, variable, or method invocation. This is effectively a log that I can add at runtime without restarting my app. It has full access to variables and everything. I can invoke a method here, although you should be careful about side effects. It's print-line debugging without the risk of accidentally committing the debugging code to Git. It's fantastic. In fact, when I see someone write print statements in the code, I cringe. This is just so much better than print. Notice that you can set a tracepoint by unchecking the suspend checkbox you see here. A breakpoint breaks by default, which means all threads are suspended. A tracepoint lets you disable that behavior. Notice you can also create a breakpoint that only suspends a single thread and not all of them. But that's a different subject. Logging is debugging, and tracepoints are exactly that. If you have a race condition, which are normally very hard to debug with regular breakpoints, a tracepoint is a perfect tool to track those. In that sense, I want to separate logging from print debugging. Logging is a very important feature for debugging and post-mortem debugging. A log is something you want in the code. It's there by design. Print debugging is something ephemeral, something we add ad hoc. As such, it makes far more sense to use it as part of the debugger than changing the code temporarily, than going through the build, compile cycle. This way, we can just add the print debugging that we want dynamically, remove them. We can't accidentally commit them to the code. We can have them as conditional statements, which means they will only print in specific cases. It's a fantastic tool that has so much potential. Method breakpoints are similar to what we think of as line breakpoints, but they have some important distinctions.
Shai, before you move forward to the next topic, there is a question about the difference between adding a new breakpoint and what jump to line plugin provides.
Yeah. So adding a new breakpoint versus jump to line.
Yes.
So jump to line isn't really so much a new breakpoint, because then you'd have to actually run the code again and trigger it. Mm-hmm. But if you're running, for instance, a unit test, and you want to rerun that unit test, then you can't really, you need to stop and then rerun everything, right? And if that test takes a while, then it might be a bit of a pain, if you're starting Spring Boot all over again and maybe lifting up containers and stuff like that, it might be a bit of a pain to stop, rerun, and hit the breakpoint again and again and again. But you just want to try the same method that you had from before with slightly different variables. So when you jump to line, you drag the execution point a bit backwards. So it's not like a breakpoint, because you're already stepping over the code. As you're stepping over the code, you're just dragging the point where you're stepping over, the instruction pointer, to a different line. And that's kind of a violation of the JVM in a way, because the JVM isn't supposed to do that. It isn't supposed to allow you to just go to an arbitrary, it's literally go to, that you're inserting in an arbitrary location. And it, as such a thing, it doesn't always work perfectly, which is why it's not a built-in feature in IntelliJ and as a plugin instead. But when it does work, it's fantastic. I'll give an example. Recently, I had a bug, and I stopped accidentally in a breakpoint. And wait, I accidentally did a step over, and I didn't mean to do a step over. I wanted to see what happened. Luckily, I had the plugin already installed, so I can just drag it back and make a do-over, essentially, right? And that's fantastic. So a breakpoint is something that you need the ability to trigger the code again, which is not something you might be able to do in all cases. Does that answer the question?
Yes, it definitely does. There's a follow-up question, which is about the jump to line. You can jump to the line that you passed, and how is that different from frame reset feature?
So I discussed that in the blog. I don't discuss it in the current presentation. It's the frame reset is a great feature.
I love it.
More coarse.
Yes.
Yeah, it's more coarse than the jump to line. So indeed, if you don't want to install that, you can use the frame reset feature, and it essentially restarts the current frame. You essentially go to the beginning of the current stack frame, which is the current method, and do a do-over, but it's just a more generic do-over than jump to line. So it's, yeah, they're the same thing, essentially, just a different UI, different experience to some degree.
Thank you, and I'll let you move forward with your presentation. Thank you so much.
Yeah, thank you. So method breakpoints, as I mentioned, they're normally emulated by the IDE. So the IDE just uses line breakpoints to simulate method breakpoints. The reason is the JVM is very slow with method breakpoints. I just try to avoid them for most cases. But there's an edge use case for real method breakpoints. Say we want to break on all the methods starting with the letter I and S in classes whose name starts with prime. This might seem far-fetched, but it's actually a case that might happen in some edge cases. So if you have an abstract base class whose subclasses follow a naming convention, and they have many related methods, you want to track everything. And this sometimes happens when you have an implementation that isn't yours, a service provider interface or something like that, like a plugin. You can do this. You can stop at every one of these entrances using this approach. Notice you can use tracepoints here and get very deep logging, such as a log or a stack trace every time a specific set of APIs is invoked. So you want to know who's invoking this plugin or something like that, you can use the method breakpoint. The value here is that you can use method breakpoints in entry and exit, which I'll talk about a bit later in this talk. Breaking on all exceptions or on some problematic exceptions is often just terrible. The IDE stops practically every second. I'll enable breaking on any exceptions to show you this. People don't do that. And the reason is we hit the breakpoint a lot. It becomes useless for any real-life application like this. Spring Boot is stopping every time it accesses a URL because the Java implementation of the URL class needs to parse a number from the header. This fails with an exception, which is caught and handled. Back then, there was no other reasonable way to parse invalid numbers in Java. Because of that, quite a lot of valid Java code throws exceptions. We can solve this with the catch class filter. We can exclude all the exceptions caught by the Java API. And this filters out these exceptions that are handled in the JDK. Exceptions in my application will still stop in the breakpoint as expected. It's amazing that this isn't the IDE default. Without it, the feature to catch all exceptions is problematic. Now, you might think, hey, I have exceptions logged to the console. Why do I need to catch all exceptions? For me, this is crucial. I often run in full screen, and an exception can just vanish within the console output. I might miss that. Then, when I restart the app, it's gone forever. I might have a problem or a bug that I'm just unaware of. With this turned on always, the IDE will stop and request focus. It will be very hard for me to miss an exception that happens and gets caught and handled properly. But I might actually want to notice, and I might want to know about that. So this is a very useful feature for me to use the catch-all exceptions. Next, I want to discuss debugging asynchronous code. One of the reasons I love Java is that it's so easy to debug. We just step into a method and we can move between threads. That's easy, but some of that is habit. In recent years, the approach of using async await and similar asynchronous techniques gained traction even in the Java realm. Thankfully, virtual threads are here to rescue us from that nightmare. But still, asynchronous code won't go away, and it's inherently harder to debug. Debuggers kept up with this to some degree. They let us see glued together stack traces to keep a sense of context. Let's dig deeper. Here we have a standard async example from JetBrains that uses a list of tasks and just sends them to the executor to perform on a separate thread. Each task sleeps and prints a random number. Nothing to write home about. As far as demos go, this is pretty trivial. Here's where things get interesting. As you can see, there's a line that separates the async stack from the current stack on top. The IDE detected the invocation of a separate thread and kept the stack trace on the side. Then, when it needed the information, it took the stack trace from before and glued it to the bottom. The lower part of the stack trace is from the main thread, and the top portion is on the executor thread. Notice that this works seamlessly with swing executors, spring async, annotations, etc. It's very cool. It just glues the part before the async call to the part after that. So if you have a swing listener, and you used it, checked it in IDs and recent history, you'd see it as if it's one stack trace with a small marker that mentions that it's actually really two stack traces that are glued together. So how does this work under the hood? And what do you do if you have a custom code that's asynchronous? The IDE works by saving the stack trace in places where we know asynchronous operation is happening, and then placing it later on when needed. How does it connect the right traces? It uses variable values. In this demo, I created a simple listener interface. You'll notice it has no asynchronous elements in the stack trace. By adding the async schedule and async executor annotations, I can determine the point where an async code might launch, which is the schedule marker. I can place it on a variable to indicate the variable I want to use to look up the right stack trace. I do the same thing with execute and get custom async stack traces. I can put the annotation on a method, and the current object will be used instead. And the way this works, it detects the variable from the current request, because in this case, we're adding listener. It saves listener as the key in a map. And the value in the map is a stack trace. And then later on, when the callback is invoked, it looks up the listener, looks up the stack trace, and glues it all together to a single request. And that's pretty cool and pretty seamless for the most part. One of the most annoying things to me is when I return from a method and have no idea what was the return value. This can happen because the developer didn't define a variable and just use the return value as an argument to an internal API, which I can step into or even use it as part of an equation. This feature solves that problem, and amazingly, it's off by default. Because this is a very common problem, I'm mentioning it here. Luckily, the IDE has an option called Show Method Return Value. It saves that value for us so we can inspect it right away. Once I check it and step out of the method, we can see the return value of isPrime appearing in the watch area at the bottom right corner. Let's zoom in a bit. Right here is the fully qualified name of the method we returned from, and the value returned from that method. Now, you might think, why isn't it on by default? It seems like such a perfect feature to have on by default, and I would agree. The reason is that it costs a bit in performance when you step over because it needs to save stuff in memory on the side and everything. I think most of us have computers that can probably manage that. So you should turn it off, and ideally JetBrains will turn it on, and ideally JetBrains would also have it on by default as well. If there's killer features you will get from this talk, to me, as I mentioned before, object marking and renders are the killer features. I absolutely love these features. Unfortunately, object marking is also one of the harder concepts to grasp in my talk. Object marking lets us declare a new static variable in runtime and store the value of an expression into it without restarting or recompiling the code. To explain object marking, let's add a watch to the current thread method. We right-click this watch entry, create a marker object. Object marking lets us give a global name to a specific object instance, so we can later use that name even when the object isn't in scope. That means I can later check if the current thread is equal to the myThread variable and get a proper result. Notice that the IDE adds a debug label suffix to the name. Still, this is the exact same variable. Now, the first thing when people see that, you think, wait, but isn't myThread underscore debug label really thread.currentThread? No, it's the value of thread.currentThread as it was when I marked the object. It took the value and it saved it to the side. But thread.currentThread will return a different value every time we invoke it from different threads. So this is a valid condition where we can actually check if the thread that we saved back then is still equal to the thread.currentThread. We essentially defined a global static variable. This is immensely useful when dealing with many objects. In the past, when I was coding back in the day in C++, we used to write down object pointer numbers on paper and then sit and look at the paper and compare it to the pointer over there. In Java, we did similar things with object identity, where we literally write the object identity on paper and wait, is that the same object as the object I have right now? Instead, I can just mark an object and then write a conditional breakpoint to stop where I need. I don't need to look at the piece of paper. I can automate this very, very common practice. I often use this with APIs like JPA, where we might sometimes have two object instances with the same identity. That means their ID value is identical, but they're two separate instances. This is really hard to detect. In this case, I just mark one object, and then I can instantly see that in this case, it's a different object instance from the original object. And that makes it very easy to detect very complex problems like the n+1 problem, etc. It's an amazing feature that once you learn how to use it, you will see it everywhere as sort of a hammer that you can use to debug all sorts of weird things. I used to love game cheats as a kid. And this specific feature makes me feel like it's cheat mode in debugging. We can show all the objects of a given type by right-clicking a thread and selecting Show Thread Objects. We can see all the thread objects in the virtual machine. We can even do that on string arrays and show all the string arrays in the JVM. Notice that in both cases, we see internal objects from the VM, even the JIT compiler thread. This is a remarkably useful feature, especially when tracking memory issues or tracking things that you don't even know. There's a search filter on the top that we can use to find objects we don't know about. We can just write Java code there and find objects just by guessing sometimes. And when you're debugging something and don't have a thread, and when I'm saying a thread, I don't mean a literal thread, but a thread in the sense of sewing, to sort of follow the bug around. And this is one of the first features I go to. And I start just looking through memory, making wild guesses, and you can instantly prove them or disprove them by seeing what I have in memory at this particular moment. And that is remarkably useful. This is something that was standing right in front of my eyes, and I didn't see it for ages. It's a feature that I'm ashamed to admit, until I actually wrote the book, I didn't know about that. Actually, a bit before writing the book, I didn't know about this feature, and it's such a basic feature. So if you hear something in this talk and think, wait, how didn't I know about that before? Well, I didn't know about some of these things before, so feel vindicated. Filtering is a very powerful feature when we have code that views arrays or collection content. We can just filter the content using an expression and reduce the noise significantly. In this case, I have 4 elements in the pet clinic demo. I narrow them down by testing against the pet ID. Notice I use this to represent the current element in the list. This is really, really useful when we're working with very large arrays. I did a lot of image processing code. And when you do image processing, you get these huge byte arrays. And I want to know, wait, how many of these values are opaque? How many of them are translucent or transparent? I want to know. And with this filter, I can instantly see these things, and I can instantly convert an array of integers to something that represents the amount of data. Is there a transparent pixel here? Stuff like that. Very, very useful. This is very versatile. If we have a list of names, we can filter it so we can only see applicable names. In this case, I filtered by an ID, but you can filter based on everything, and it's really, really helpful. Streams in Java 8 are probably how most of us do these sorts of things. If you're not familiar with that, then you probably should be. But if you're coming from Kotlin and other technologies like that, then streams in Java 8 are constructs inspired by functional programming that let us chain processes and process a stream of elements. They're pretty cool, but one of the problems in them is they are harder to debug than typical loops. IntelliJ ships with a stream debugger that you can find in this button that I'm pointing at with a mouse. When you press it, you need to be positioned on a stream in the debugger. As you can see, I am in the line above. Pressing the button launches the stream debugger. On the top, you can see the stages of the stream expression. Notice that as I traverse through the stages of the expression, the objects change and draw a line between their original mapping to the new one. Initially, the list was of visits, and now we see the conversion to pets in each visit. Since the final stage is a set, we will only get one instance of each pet. That isn't shown here. The advantage here is that you can see the entire process in a single view that you can take back and forth, unlike a loop which you can normally debug by stepping in the debugger. This view here is a bit more complete. Now, this is a fantastic tool, and also it's a representative of time travel debugging, which is an amazing concept that allows you to essentially view projects, view a debuggable application sort of in a bird's eye view. And it's enabled because streams don't really carry state in the same way that normal code does. Now, if a stream has a side effect, which it normally shouldn't have, but Java can't physically guard against that, then the stream debugger will fail. You will get a weird error that doesn't work for some reason. So if that happens, make sure that your stream doesn't change local variables or do something of that type, which is very problematic. Rendering is, as I mentioned, one of my favorite features, and it's a fantastic feature that people just, it blindsides people. We think of watch expressions as this fixed thing, but when we're debugging a huge system, things can become tedious. A debugger can only show what it knows about, and for the most part, it's just guessing. With renderers, we can determine how an element is displayed in the watch, but we can go much further with renderers. To get started, we can customize the renderer through the right-click menu here. For the most basic customization, we can toggle and enable multiple features within this dialog, and then press apply to instantly see them in the variable view below. I can see the declared type of a field. We can include fully qualified names for class files. We can see static field values. We can include hex values for primitives by default, and just so much more. It's a fantastic tool, and I urge you to explore all of the features that we have here for debugging all sorts of for viewing all sorts of weird details about fields that we see in the watch area. It's really illuminating about what is possible within the IDE. But this is just the first tab and the simplest part of it. The cool part is the next part. Renderers slow down program execution. So if you feel that step over is slow, just mute them like this. Then you can see individual values for renderers by clicking the specific item. Let's take this whole thing up a notch. We have a repository instance, and the visit, before I actually proceed with that, if you don't work with Spring Boot, then repositories are essentially very similar to database tables conceptually. They let you query a table and get back JPA entities, essentially objects representing rows within the table. And the problem with repositories is that they don't have that much of a state. So when you look at them in the watch area, as you can see in the bottom, we have a repository instance. And the visitor repository variable below, it just doesn't provide valuable information. It's just the toString value. And the toString value is just an object identity value. It doesn't give us any information. What we can do here is we can add a renderer that applies to JPA repository, which is the class type of one of these repositories and is the base interface for that specific instance. Then we just write the expression to represent the rendering here, how we want it to appear in the watch area. will show the number of elements in the repository using the count method. Essentially, this will count the rows within the table. Notice I don't provide an object instance. The IDE automatically runs the code in the context of the object. You can also use this to represent the rendered object. You can run this on demand, which makes sense for expensive expressions, or you can use something similar as I showed before, where render requires a click to actually show the value. Look at the visit repository variable preview and see the value instantly adapt to these changes, right? The view repository is rendered with the right string containing the element count, but it isn't properly expandable. So right now we have the count and the size, but it's not expandable like that. The solution is that we can execute the find all method on the expansion, and that essentially queries the database table and returns all the entities from JPA. And that way you can actually see the content of the database right in the watch area below, which means now I can look at a visit repository and see how many elements it has, and also expand it so I can see every element within the database. And that's fantastic. I can also make a defined expression that indicates if the data is expandable using the count method, so I don't waste time invoking the find all method every time. Let's talk a bit more about custom rendering. You'll notice that everything looks exactly the same. We have the exact same logic as we had before. The numbering, the list of entities, etc. But when we open the list of renderers, in this case, it's blank. There are no renderers because I didn't use the same approach to get the same result. How does this work without defining a render in the IDE like I did previously? What's going on? In this case, I used code annotations to represent the renderer. This way, you can commit the renderer to the project repository, and you don't need to configure individual IDE instances. This is pretty simple. I added a dependency to the JetBrains annotations library into the POM. This is the same library I used previously when I wrote the asynchronous code that included those annotations. This library has no impact on your runtime performance. It's strictly useful during debugging and compilation. It shouldn't cost anything to add it. We add an import to the renderer and then scroll down, and we added a simple renderer annotation code. Notice that this is pretty much the code I typed in the dialog, but this time it's used in the annotation so my entire team can benefit from the improved view of the repository objects. Now, this is fantastic. That means that every member of my team can see all of that information. Now, why is that so useful? When I show this to people, sometimes their instant reaction is, well, I've got a toString method. Why not use a toString method that returns all of that information? And the thing is that a toString method is very, very dangerous. Say you accidentally log that toString method. In that case, you might cause a significant performance penalty because this causes a query into the database, which is very expensive, but not a big deal if we're inside the IDE debugging. We don't really care in the IDE. It's fine. We can cost a bit in performance to get better insight. But if we're in production and we have a toString method and we just do a query on the database every time that something gets logged accidentally, whoa, that's really bad. But it gets worse because the database might include private information in production. So you might be pushing private user data into the database and might be breaking some serious laws in that case. And I'm sure no one here wants to go to jail because of bad debugging practices. So don't use toString methods in the ways that I showed here. Use renders and keep yourselves out of jail. Best tip in the presentation, hopefully. If I can save you from jail, I did my part.
So Shai, we
Yeah,
have a question on what you just showed. So the
yeah.
question is by Starflex Technologies, and they're asking, will this annotation not pollute the code base, and how are these translated in the compiled code?
So great question. To be clear about that, the annotations will be part of your code, obviously, because you write them. So they will go into Git. You will have the dependency on the JetBrains annotation library, but they will not impact anything in terms of performance because these are compile time annotations. That means the annotations will exist in the bytecode. They will be visible in the Java source code. They will be visible there. The IDE will know about them and will use them to define the renderer. But in runtime, they will have zero impact on your bytecode. The bytecode will keep executing. Nothing will happen there. And unless you're running production within the IntelliJ debugger, which I seriously hope you don't, hopefully, fingers crossed, then zero impact for that. And that's the important reason for using renderers, whether you're defining them in the IDE or defining them in the code. And I recommend defining them in the code because karma, you're helping all of your team, not just yourself. Because it's great to be the world's best debugger. It's way better to be a team player who helps everyone be the world's best. So if you're building a JVM library or something like that, adding these annotations will not just improve your library, it will improve the lives of everyone there that's using them. For instance, in our Codename One project, which lets developers write applications for mobile platforms using Java. It's an open source project available for everyone for free. We added annotations for the async code right into Codename One. Zero impact, doesn't impact anything at all. But when you're debugging, now every time you get a listener, you'll actually get a full stack trace, right? We thought about adding renderers, but we got a bit lazy. Maybe if someone wants to contribute that, be my guest. But it's a remarkable feature, and I hope more people use it. I used it a bit aggressively here, by the way, because doing queries on the database every time you step over the code might have some serious side effects, even in debugging. So you might not want to do that, but it's fantastic. And I hope you do that, and I hope you do that with the annotations, because team player.
Thank you so much, and I'll let you move forward with your session. Thank you.
Great, thank you. When we think about memory debugging, we usually think about profilers, which do have some functionality for that, but the standard debugger has some amazing capabilities. Memory debugging is a very expensive tool, so it's off by default. When you don't need it, disable it so your debugging performance won't suffer. Unlike some previous examples where I showed things and I said, oh, our computers are fast enough, this isn't the case. Here you will feel it, even in a strong computer, when you turn that on. Let's start by launching the memory view from the IDE UI menu. Notice that the memory view is empty by default, even after we launch it. This keeps the IDE responsive. In order to see the actual objects in RAM, we need to click the load link in the center. Once loaded, we can see the instance count for every object. This helps us get a sense of what exactly is taking up memory. But that's only part of the story. When we step over, there are allocations happening in the methods we invoked, and possibly in other threads. We can see the difference between the current point and the one before when we look at the diff column. We can double-click an individual entry and see all the instances of the given object, which is a remarkably powerful feature. We saw some of that previously when I showed it earlier. But this is tedious. I have a fast machine with lots of RAM. I can just enable update loaded classes on debugger stop. Don't do that at home necessarily, but in this case, I will do that mostly for demo purposes. But it will be unpleasant if you run like this all the time. This will no longer require that I press load explicitly, but only do that if your machine is a monster, as I said. Track new instance lets us explicitly track the individual allocations that are going on between 2 points. We can enable that by right-clicking any non-array object and enabling this option. Once enabled, we see a small watch sign next to the tracked object. But there's a lot more involved. As we continue the execution, I can now see only the objects allocated specifically in this diff and can understand exactly what happened in terms of RAM. So if I have a line and I stepped over it with this turned on, I can see the objects allocated between this line and the next line. And that's important if I invoke libraries deep inside and I want to see what did that library do? What did it allocate? Why did it allocate that? That gives me a sense of what exactly is going on. I can click on an individual object and see the stack trace that triggered it all the way up to the literal call to new. And that's fantastic because I can look at this object, and if I have a memory leak that I can see in the profiler, which is usually the case, I can see a type of object in the profiler. Sadly, it's usually byte arrays and stuff like that, but sometimes it's not. And for those cases, I can just place a watch and actually see the stack traces that triggered everything. And that way I can go back and proceed with standard debugging for these things and understand a specific object instance, where it came from, what specific values it had. And I can also use the filter feature that I mentioned before to find a specific object that might be problematic. So this is an amazing supporting tool for profilers, and sometimes even a replacement for the profiler in this particular case. Threading issues are notoriously hard to debug, but this reputation isn't always justified. Once you understand the basics, you'll find that most threading issues have some similarities. Let's start with the basics of thread debugging. In the stack frame, we can look at all the current threads in the combo box above the stack frame. We can toggle the currently selected thread and see the stack for that thread and the thread status. Notice that here we chose to suspend all threads on this breakpoint. If the threads were running, we wouldn't be able to see their stack as it's constantly changing. We can enable the threads view in the right-hand side pull-down menu to see more. As you can see, viewing the stack is far more convenient in this state when working with many threads. Furthermore, we can customize this view even more by going into the Customize Thread view and enabling additional options. The Thread Groups option is probably the most obvious change, as it arranges all the threads based on their groups and provides pretty deep view of the hierarchy. Since most frameworks arrange their threads based on categories in convenient groups, this is often very useful when debugging many threads. Other than that, we can show additional information, such as the file name, line number, class name, and argument types. I personally like showing everything, but this does create a somewhat noisy view that might not be as helpful. Now that we switched on the grouping, we can see the hierarchy of the threads. This mode is a bit of a double-edged sword, since you might miss out on an important thread in this case, but if you have a lot of threads in a specific group, it might be the only way you can possibly work. The first step of debugging a race condition is a method breakpoint. I know what I said about them, but in this case, we need them. Notice the return statement in this method includes a lot of code. If I place a breakpoint on the last line, it will happen before that code executes, and my coverage won't include that part. I only use it for the exit portion, because if I used it for both, I'd have no way to distinguish between exit and enter events. I want to log the entry to the method, which I can do with a regular trace point. But to log the exit, I want to place a breakpoint after the method completes. And for that, I need the exit for a method breakpoint. I make this a trace point by unchecking the suspend option, and then I log the name of the thread. I now do the exact same thing for the line breakpoint on the first line in the method. A line breakpoint is fine, as I mentioned, since entry to the method makes sense here. I change the label and make it also into a trace point instead of a breakpoint. Now we can look at the console. I can copy the name of the thread from the first printout in the console and add a conditional to reduce the noise. If there's a race condition, there must be at least one other thread, right? So let's remove one thread to be sure. And the way I remove it is I just check the current thread, I check its name, and I compare it to the name of the first thread, and then I can see if such a thread exists. I filter it, and then I'm essentially done. Now, going down the list, it's obvious that multiple threads enter the code. That means there's a risk of a race condition. Now, it means I need to read the logs and see if an enter for one thread happens before the exit of another thread. This is a bit of work, but it is doable. Obviously, it doesn't necessarily mean there's a full race condition because there needs to be changes to state, but you get my point. This will allow us to see if a race condition is even an option because there's no breakpoint going on. It's all trace points. The next step is debugging deadlocks. Here we have two threads, both of which are waiting on a monitor held by the other thread. This is a trivial deadlock, but debugging is trivial even for more complex cases. Notice the bottom two threads have a monitor status. This means they're waiting on a lock and can't continue until it's released. Typically, you'd see this in Java as a thread is waiting on a synchronized block or a lock. You can expand these threads and see what's going on and which monitor is held by each thread. If you're able to reproduce a deadlock or a race condition in the debugger, they are both simple to fix. I talk a lot more about the ability to find these cases even when you can't reproduce them in the debugger, but that's subject for a different talk where you can connect the debugger to an already running application and do work there and also get additional information using external tools. And with that, I've finished the talk, and I hope you enjoyed it. And I hope you have many questions regarding the subjects that we talked about today.
So first of all, thank you so much, Shai. That was an amazing session, and I learned a lot. And before I talk much about the session, for everyone watching the session, please use either the QR code which is shown on the screen or the link, and please share your feedback. It's amazing to hear from you what you think about the session, and it definitely helps us to improve the future session that we host. And with that, Shai, so I think there were not a lot of questions, and there was one comment which I'd like to say. It was about when you talked about the renderers. So one comment was, I think renderers deserves a separate session because yes, it has a lot.
Yeah, there's a lot to unpack there. Definitely. I feel I didn't do them justice, not renderers and not object markers. Marking, because both of these are subjects for a session of their own. I very much agree. But I think these are things that need to sink in as concepts. And I'm not sure if talking further about them and droning people to sleep with my voice would improve the situation. You need to sleep over this and then get a follow-up session.
Makes sense. There was another comment by Kamal Sorsal, and he mentioned also one thing I take away from the session is to be able to distinguish the object ID in the conditional breakpoint.
Yeah, that's the object markers are so fantastic. I absolutely love them, and I think I think about so many cases in the past where I used pen and paper to debug these sorts of things, and I don't think that existed in those IDEs anyway. So I didn't miss on something. It's a feature I only know, as far as I know, only IntelliJ has that feature. And by the way, in my site, I don't want to talk about that here because it's a JetBrains channel. But I have in my site a comparison between IntelliJ and a different IDE who will go unmentioned in terms of debugging, and the difference is stark in favor of IntelliJ in terms of debugging features. So, and I want to say I'm not getting paid anything by you guys. It's fantastic work on the debugger front that was done in the IDE. So kudos to the team.
I confirm about the payment. No payment is being done. No transactions, no monetary transactions.
Yeah. Yeah.
So I don't have more comments and questions because the ones that they were, I asked them to you, and also we have a developer from the team who was answering some of the questions. So I just wanted to show some comments about appreciating your session. This is so nice. And I think if I had to choose from the feature that really stood out from your session was seeing all objects in the virtual machine. There was the filters, and I think the clear winner was the stream debuggers. So these are heart emojis and oh my god, I'm blown away emojis. And so this is another comment which says collection filter is amazing. Wow, I did not know that. Again, there's a
same.
heart
I
emoji.
didn't know either. So same.
Right. I remember I created a tweet a long time ago on stream debuggers where I said if you are not using stream debuggers in IntelliJ IDEA, you are not debugging your streams in a fun way, and that was something that was liked by a lot of people. So I agree.
It's revolutionary, and it's one of the features. I wrote a chapter in my book about time travel debugging, which is sadly not yet a field that caught on. I always say, next year would be the year of time travel debugging, and it doesn't happen. But I think stream debugger is sort of harbinger of what's to come.
Yes.
It's a fantastic tool. It's that's what time travel debugging is. The problem is time travel debugging is such a huge thing and so impractical. But it solves a specific point in a specific area, and that's what we need. So if JetBrains developers, debugger developers watching that, more of that's definitely the right direction. So.
Thank you so much. So there are more comments. Siraj is saying, this is great. Never heard about this before. So this was again about the stream debuggers. And Van Troll says it's a great feature. And again, Tiago says it's an amazing tool. And there was one thing. Yes. So what a wonderful demo from a guru. And there was another by Fabrizio, and he's a very interesting session, and he had to leave. So thank you so much, Shai.
Thank you all.
It was a pleasure to learn from you. Absolutely a pleasure. Thank you so much.
It was a pleasure being here. Thank you for having me.
And thanks to everyone who attended the session today, for asking questions, for participating, and yes, for learning. So here you can see all the social links for Shai and for IntelliJ IDEA. If you have any questions for us or for Shai, please feel free to reach out. And do not miss on the next session that we have next month, which is going to be a session on AI. So that's again going to be an interesting session for you. And Shai, before I close the stream, if you have any closing comments, please feel free to share.
Well, if you like that, there's a lot more in my channel and debugagent.com. And feel free to contact me on socials and ask questions there. I'm always available. And I'll try to answer in the YouTube recording if I get a chance and remember to do that. Ping me about that if I don't. Or
Yes,
tag
and
the
as
debug agent.
yes, you can tag him on Twitter or ping him. So yes, do that. And again, thank you so much, Shai, and thanks everyone. And until next time, bye bye.